Hello everyone. Today I will talk to you about Lewin's circuit paradox. This paradox was made famous by Dr. Walter Lewin. He was a former professor of physics at MIT. The paradox goes as follows. We have a closed wire loop. This wire loop is exposed to a magnetic flux density, denoted by B. The magnetic flux density is vertical. The loop is also loaded by two resistors, R1 and R2. Here, we would like to measure the voltage across the loop. For that reason, we have two voltmeters, one on the right side and another one on the left side. From the basic circuits theory, we know that the voltage must be equal on both voltmeters. However, in the actual experiment, we see two different readings on the two voltmeters. The problem is, Kirchhoff laws seem to fail to analyze this scenario. Is this true? And how to explain such a problem? The approach that I'm going to take here will go as follows. First of all, I will apply Faraday's law in order to find the electromotive force, EMF. Next, I'm going to obtain an equivalent circuit. This equivalent circuit will allow me to apply Kirchhoff's laws. According to that, I will be able to find the voltages and currents inside the loop. But before we start analyzing our paradox, let's first of all remind ourselves about Faraday's law. Faraday's law is stated as follows. The EMF is equal to the closed contour integral of the electric field dot dl along the contour, and that is equal to minus partial by partial t, the surface integral of the magnetic flux density dot ds, normal to the surface. If we take a look at the figure on the right, we can see the contour defined as follows. Of course, there is a surface created by this closed contour, we call it S, and according to that, we can declare a normal unit vector N. And of course, we have a magnetic flux density that is crossing the closed contour. In this example, everything follows the right-hand rule. However, as you know, we have the minus sign in front of the integral partial by partial t integral s b dot ds. This is known as Lenz's rule, and for that reason, we have to be careful when to apply the right-hand rule and the left-hand rules. I will leave this to you to figure out how to apply Faraday's law correctly. In addition to that, Kirchhoff's laws are usually stated as follows. KVL, which is the sigma V equals 0, and KCL, which is sigma I equals 0. In this example, we would like to examine how to apply Faraday's law to our loop. In this simple scenario, I have removed the voltmeters from the picture. This will simplify our calculations and will help us understand how to apply Faraday's law correctly and how to find the equivalent circuit. Of course, in this scenario, we have to make assumptions like assuming ideal wires, resistors, and voltmeters. Also, we will assume that the magnetic flux density only exists inside the loop. no magnetic flux outside the loop. Of course, this magnetic flux is uniform everywhere across the loop. If we apply Faraday's law correctly, we should be able to find this equivalent circuit. This equivalent circuit shows an EMF or a voltage source inside the loop. Of course, this equivalent circuit means that there is no magnetic flux density inside the loop. However, I kept the highlighted area just to remind you where was the magnetic flux density. And from then, we can basically apply the circuit laws and find the voltages V1 and V2. And since our magnetic flux density is uniform inside the loop, the integral reduces into a multiplication. And all what we have to do is to take the derivative of the magnetic flux density with respect to time. In order to find numerical expressions for the EMF and the voltages inside the loop, we have to describe the magnetic flux density with respect to time. In this case, I have chosen this expression in which the magnetic flux density increases from 0 to a value of B0, and there is a time constant tau. For simplicity, let's assume that B0 and tau are both greater than 0. If we apply the Faraday's law, as stated previously, and considering the expression from the previous slide, we should be able to find the EMF expression as follows. The EMF is nothing but V0 multiplied by A, which is the area inside the loop, divided by tau. And of course, there is the coefficient e to the minus t divided by tau. This can also be written as d phi by dt, in which phi is the magnetic flux multiplied by e to the minus t over tau, or simply it can be V0 e to the power minus t over tau. Applying the voltage divider circuit analysis, it is easy to find V1 and V2 expressions as follows. If you have watched Dr. Walter demonstration, he applied the following numerical values. d phi by dt equals 1 volt, R1 equals 100 ohms, and R2 equals 900 ohms. If we use these values, we obtain the following voltages across each resistor. The next step is to consider the voltmeter measurements. And for this case, I decided to place the voltmeter inside the loop and see the effect. This choice makes the analysis a little bit easier and more intuitive. We will apply the same procedure if we put the voltmeter outside the loop. As you can notice here, this voltmeter divides the loop into two smaller loops. The smaller loop has an area of alpha A. This is the loop to the left. And the wider loop has an area of 1 minus alpha multiplied by A. If we set this parameter alpha between 0 and 1, we can slide this voltmeter from the left to the right, from R1 all the way to R2, allowing us to study the voltage change across the loop. In addition to that, we will set T equals to 0, and we will only look at the voltages at that time for simplicity. The circuit model in this case should look like this. Because we have a voltmeter with probes and wires, they splitted the circuit into two smaller loops, and each loop has its own EMF. And because we have oriented our voltmeter vertically, it was easy to find the equivalent EMF source on each loop. And of course, we can use the parameter alpha. In this case, the voltmeter reading should be V0 multiplied by alpha minus R1 divided by R. We obtain this expression if we use Kirchhoff's law on the left loop. If we do the same thing on the right loop, we find V0 multiplied by alpha minus 1 plus R2 divided by R. And indeed, the two expressions are equal, and you can verify this by yourself. The most important result is that the voltage across the loop in this scenario will depend on the location of the voltmeter. If we use the previous numerical example and we take the same values and we set alpha equals 0.5, which is in the middle, we should find that the voltage at time t equals 0 is equal to plus 0.4 volt. Now it is the time to study Lewin's paradox. We can apply what we have learned from the previous examples, and we can place the voltmeters outside the loop. We shall use similar techniques, and it is possible to split this analysis into the left voltmeter and the right voltmeter separately. Of course, using the superposition principle, we can find the overall behavior. If we consider the voltmeter which is connected to the left side of the loop, in this case, there is an induced EMF which equals alpha, the EMF on the major loop. And if we perform our analysis correctly, we should find the voltage across this voltmeter, I call it here V left, equals to minus V0 R1 over R. And the most important result here is that this reading is independent of alpha. Everywhere the voltmeter should read minus 0.1 if we use the numbers from the previous example. We can apply similar analysis to the voltmeter on the right, and as you can see that the voltage in this case, we call it V right, equals plus V0 R2 over R. And again, it is independent of alpha. Everywhere the voltmeter reads V right equals plus 0.9 volt. Now we can conclude that if we run this experiment in our lab, we should read two different values on each voltmeter. And the reason for this to happen is because the loop created by each voltmeter during the measurement will affect the value of the voltage. In addition to Dr. Lewin's experiment, we can also try to measure the voltage across the loop in this setup. This setup, I call it setup 1. It will measure the voltage across the loop. However, the resistors are excluded from the measurement. And as expected from the practical experiments, that the voltage on the voltmeter is always 0, using the same previous analysis. However, if we make this setup in which the two resistors are included in this fashion, we will find that the voltmeter will always read V0. If we use the previous numbers, V will be always 1 volt. After this demonstration, I would like to end with the following conclusions. First, indeed, Dr. Lewin's circuit measurements are correct, and they also match our analysis. However, this paradox is a result of misunderstanding of Faraday's law. By ignoring the induced EMF in closed loops. Any closed loop, including the voltmeter probes and wires, would exhibit induced EMF. And this is the root cause of the paradox or the confusion. In addition to that, Kirchhoff's laws are indeed correct and valid as long as we apply them correctly. And finally, we can consider a more general treatment for this problem. And this can be done if we assume the magnetic flux to be any arbitrary distribution inside and outside the loop. We can also make the loop to take any arbitrary shape instead of this rectangular shape. Finally, I would like to recommend the following YouTube channels. The first channel is by Dr. Lewin himself. You will find his lectures, his explanation, his demonstration, and experiments regarding this problem, and the rest they have demonstrated these experiments, and also they provided a thorough explanation for the physics behind this paradox. Also, I would like to recommend you to read Lewin's Circuit Paradox, which was written by Dr. MacDonald from Princeton University. Thank you for watching.